Hi there! This video is the third part of the tutorial how to play a video on Arduino Uno. In the previous episode we showed you how to hack this module to enable 8 MHz transfers. In this video we will analyze which connection is better for our purpose, SPI or USART in SPI mode. We will also take a look at other issues which induce performance loss. Let's go for the next hack! Last time we were able to communicate with the SD card at 8 MHz. However, if we look at the transfer rates, we will notice that these are actually very disappointing. In fact, we got less than 400 kilobytes per second. Why is the transfer so slow? We identified some of the main causes. We have some software overhead in our program. In fact, our software performs other operations beside calling the function which actually reads from the SD card. The FATFS library also has software overhead because it needs to check and update its internal state. The SD card also has overhead. In fact, we need to send via SPI some command bytes to initiate the read operation. Furthermore, after the command has been sent out, the SD card takes time before it can actually send data. This time is product and model dependent. Even if the majority of the datasheets state that the typical delay is some milliseconds, we found out that this time is much shorter on many cards. These first three overheads can be mitigated by reading many sectors at once instead of just one. This is what we will do in the next episode. Another issue is the overhead due to the file allocation table file system structure. In the FAT file system, each file is stored as a collection of many segments of contiguous sectors. These segments are called clusters, and they may or may not be contiguous each other. Therefore, if we finished reading an entire cluster and we want to read the next one, we don't know a priori where the next cluster begins. In order to know which is the next cluster on the file, we must read a particular table, the file allocation table. As an example, let's consider this very simplified file allocation table implementation. We have just 10 clusters and 2 sectors per cluster. The file allocation table, shown on the top, defines chains of clusters, the files. For each cluster number, which corresponds to the table index, we store the index of the next cluster on the file. In this example, if a cluster is the last one of a file, we store an E. Let's suppose we want to read the file number 2. Let's also suppose we already know that the file number 2 begins with the cluster number 3, i.e. at sector 6. Therefore, we start reading such sector. Since we have 2 sectors per cluster, we know that the next sector to be read is the number 7. However, after we finished reading the last sector of the cluster number 3, we need to know which cluster we must read next. Therefore, we read the file allocation table at the index 3, which is the number of the last cluster we read. The table indicates that we need to read the cluster number 4, which starts at sector 8. The next sector is the number 9, as it belongs to the same cluster. Now again, we finished reading a cluster. We must read the table to know which will be our next cluster. Since we were reading the cluster number 4, we look at index 4 in our table, and we obtain 7, which is the next cluster to be read. The corresponding starting sector is number 14. As you can see, this time the cluster was not contiguous, like in the previous case. The procedure repeats until we get to the end of the file. Each table read operation is a normal sector read. The smaller the cluster size, the more often we need to read the table, and the slower the overall performance. For instance, with 16 kilobyte cluster size, we need to read the table every 32 sectors, as one sector is half a kilobyte large. In other words, the read speed is about 3% slower because of the additional read operation. If the cluster size is 4 kilobytes, the penalty rises to more than 12%. Let's go back to the list. The next issue is represented by the interrupts, which are called each millisecond to measure the elapsed time. Another performance loss cause is the SPI Read code, which was not optimized in the FAT-FS library for AVR microcontrollers. Let's analyze the original algorithm on the FAT-FS example. We write to the SPI bus, we wait until the transmission completes, and then we read what the SD has sent out. The problem is here. After we write to the SPI, we just do nothing useful for more than 16 CPU clock cycles. That's a lot of wasted time. The optimized version seems to be more complicated, but really it isn't. It takes advantage of the double buffered SPI register in read mode. To understand better the program flow, we graphically unroll the loop. After we write, we read the previously received data, which is still in the read buffer, even if new data is being received in the meantime. We also perform other operations, such as decreasing the number of remaining bytes and checking if there are any bytes left. At the end of the cycle, we must wait, as we don't have any more useful things to do. Still, in this case, we just wait for a much shorter time. Let's go back to the list. Is it all? No. We have one more thing that induces a lot of performance loss. The SPI transmit register is not double buffered. Is this a big problem? Yes, it is. In fact, if we look at the clock signal with a scope, we see that there is a huge gap between two consecutive bytes. Therefore, without other kinds of overhead, we could only achieve less than 5.5 megabits per second, even with optimized code. Let's analyze this in detail. This is the SPI of the AVR. It has a transmit shift register and a status register. The transmit shift register is not double buffered, therefore we cannot write to it when transmission is ongoing. The status register has a flag, SPIF, which informs us when the transmission has completed. Let's consider the piece of code on the top left corner. The red arrow is the position of the next instruction that will be executed. The shift register is empty and we can write to it. Now the transmit register contains data. We cannot write other data, so we wait using loop until bit is set function. In the meantime, the SPI shifts out the data while we wait. Now the data has been sent out, and the SPIF is now 1 as a notification. Let's pause our system. When the SPIF flag becomes 1, we are still in the function loop until bit is set. On the right, we wrote in a human readable language the instructions this function is made of. The SPSR register is copied to a CPU register. Now, the bit 7 of that CPU register contains a copy of the SPIF value. Then we read that bit and we jump out of the loop if it was 1, otherwise we begin the loop again. We don't know which instruction the CPU is executing when the SPIF becomes 1, unless we perform a cycle-by-cycle detailed analysis as we did in our website. However, for sure, all of these 3 operations must be executed after the SPIF becomes 1 in order to jump out of the loop. This translates into a transfer gap, i.e., the SPI is not sending any more data for a certain amount of time until we write again to its transmitter register. Now we'll write again. The gap will increase in length as the transmission will start next CPU clock cycle. As you can see, the effective data rate is much lower than the expected 8 megabits per second. From the scope, you'll find that it is less than 5.5 megabits per second, even in the optimized version. The final data rate is smaller because we haven't dealt with the other problems on the list yet. You might be tempted to reach the maximum 8 megabit per second speed by writing data to the SPI register each 16 CPU clock cycles, i.e. once per microsecond. However, it turns out that due to the particular SPI implementation, you can send data only every 17 CPU clock cycles, and not just 16. In other words, you cannot achieve 8 megabits per second using the SPI, but just 7.5. This may sound good, but it's still 7% less than the maximum speed. The solution is to use the USART in SPI mode. It has a double buffered transmit register, that is, the data register UDR0 is separated from the transmit shift register. It has also a status register in which the flag UDRE0 tells us if the data register is empty, i.e. ready to accept new data. Let's consider the code snippet on the top right corner. As soon as we write to UDR0, the data is copied directly to the shift register, because in this case it was empty. Then we jump into the loop until bit is set function. Even if the flag was already 1, we still waste some clock cycles, as we did in the SPI case. Therefore, in the meantime, some data bits are being sent out. Now we arrived to another write instruction. Let's see what happens. The data is moved to the transmit register, but this time the shift register is full. Therefore, UDRE0 flag becomes 0, and from now on we must wait until the shift register has shifted out all of its bits. The shift register has now shifted all of the bits, but before the end of the last bit of the previous byte, some magic occurs. The USART automatically copies the UDR0 to the transmit shift register. In this way, in the next clock cycle, we are ready to send other data, without gap. Now the USART has moved the content of UDR0 into the shift register. UDRE0 flag becomes 1. Telling us that the data register is empty. And now there is another important fact. Even if the loop until bit is set function takes some time to return to the program flow, we just don't care, as in the meantime the USART is still sending the previous data. Unlike SPI, no gap will be generated. As you can see, the effective data rate is 8 megabits per second, and this is done without any software trick. Well, enough theory for today. Let's implement the USART test code. Unluckily, since we are using the USART to communicate with the SD card, we cannot send any data using the serial port for debug. We also disable the interrupts, as we have no way to print out the elapsed time. We will use the scope. We modified the FATFS to use the USART instead of the SPI. We also modified the schematics for the USART implementation. The USART in SPI mode is very similar to the SPI. Instead of MISO and MOSI, we use RxD and TXD. The SPI serial clock is replaced by the USART clock, which is PD4 or IO4 on the Arduino Uno. Of course, we can use any I/O pin as chip select. Let's build our test circuit. We connected also 3 probes in our circuit. As you can see, the test passes and there is no gap between consecutive bytes, i.e. we get the 8 megabit per second data rate. Furthermore, we can measure the time taken by the high-speed test, which is the time between the blue LED turning on and the time the red LED goes off. We get 1.47 seconds, which corresponds to about 600 kilobytes per second. This effective data rate is much slower, as, again, we have not dealt with other issues on the list yet. These will be covered in the next video. As we said, using the USART prevents us from sending data using the serial monitor. Furthermore, we need to disconnect our circuit when programming. As a third drawback, we will see in the next video that we will have to put a jumper between the reset and the ground when not programming. This is to avoid contention between the programming IC and the other peripherals such as the ATmega328P, the SD card and the display. This concludes this episode. We hope you found it useful and clear. Don't miss the next episode, as we will finally show you how to play an unlimited length video at 20 frames per second. As always, you'll find everything in our website, next-hack.com. Please rate, comment and subscribe to this channel. Thanks for watching. What's your next hack?